Today's technical session is resilient geosynthetic solutions to counter soil erosion. In today's session, we are having three technical experts and we'll be having Q&A session after all the three presentation we have in the end. Now, about FIB, this series, supported by FIB, reflect its ongoing commitment to excellence in engineering. FIB, a not-for-profit association with members in 104 countries, is dedicated to advancing concrete construction's technical, economic, aesthetics, and environmental performance. Their contribution through FIB bulletin, events, workshop, and courses are invaluable. About Officina Ferry, headquartered in Italy, we are a 140-year young organization with sales spread across 130 countries with more than 3,000 employees, 23 factories, and 70 subsidiaries. Ferry Indian subsidiary was incorporated in 1998 as Ferry Environmental Solutions Private Limited. We are eager to contribute to geotechnical community by advancing knowledge in geotechnical and allied fields of sustainability. We have been associated with some of the most prestigious construction projects across the country. Now, to begin with our first session of first today's session, I would like to invite Mr. Himanshu Kotak. And Mr. Himanshu Kotak is founder and director at C5 Consult Private Limited and geotechnical professional with more than 15 years of experience. He holds MTech in Geotechnical Engineering from IIT Kanpur and BE in Civil Engineering from MSU Baroda. His career encompasses of broad range of infrastructure sectors such as highways, railways, airports, port marine, landfills, thermal plant, and many more. So now I would like to call Mr. Kotak to the dais, please.
Thank you, Mr. Sumit. I would simply share the screen and then we can start with the presentation. I hope the screen is visible.
Yes.
Yeah. So I'll be briefing about the soil erosion in the beginning, and we'll be focusing more into the technical things, where we'll be discussing the different reasons for the soil erosion. What are the different generally adapted schemes for erosion control in mainly in India? Then we'll be discussing few of the cases where typical failure of erosion control schemes. We often observe into the our projects basically. Again, with that, we'll be trying to identify the importance of problem identification before we suggest any kind of solutions, and will also be focusing into the typical reasons where erosion control scheme measures which are taken on a project, it generally results into the failures. So we'll start with the basic things, like what is the you can say the soil erosion. So as you can see in the picture, we can say that it's a process where detachment and transportation of soil particle occurs by different agents such as wind, water, and gravity. So when we talk about this particular portion, what in general happens is, we have um soil erosion due to one or the combined elements of wind and water, typically in the case of embankments where the due to soil erosion soil mass loses from the embankment, detached transport to the other locations, which results into formation of gullies cuts into the embankments, and this gives birth to a newer, you can say, geometry which might not be stable to the projected planning, and that might result into the overall slope failure. So this is the brief about the soil erosion. Now, as we discussed, we have three main agents, which are wind, water, and gravity. These three agents normally work in tandem with each other, and when they are, working with each other simultaneously, they can create a great amount of damage to the infrastructure related embankments. This theory is applicable to all kind of, you can say, in a way, structures, whether it is for the railways, roadways, whether it is open lands. You can have the hilly area, but we'll be trying to understand in context of embankment, either in cuttings, or you can have even this is applicable to cutting sections as well. I mean, so wind erosion is typically quite common in case of areas where the wind velocity is very high, where the type of soil is fine, cohesionless. When we say cohesionless, typically silt and fine sand are the main two categories which are affected by wind erosion in general, where the soil particles are typically blown due to the wind. So, this is typically a critical factor when we have exposed slope, which are not protected, which are made of non-cohesive soils, and where the wind, there is a quite open land, open area, which can allow the huge amount of wind to accumulate and allow the erosion kind of phenomenon. When we talk about the uh, wind erosion, there are three main factors which is of higher importance. One of them is speed, another one is the direction, and third is the turbulence and distance from the ground surface. So these three are typical, prime importance factors in case of wind erosion. Typically, the speed of the range 12 to 15 kilometer per hour and about 150 mm above the ground level. It's the threshold value where you have, if you have the grain size of 0.10 mm to 0.15 mm, then this is the most, you can say, kind of suitable condition for wind to erode the soil mass. And based on, see, there are so many, you can say, the many people have done the different studies, and they have come up with the research where they have given, a different correlations. One of the correlations which are given at the research is, when you have a particle size diameter of 0.42 mm, which is 420 micron, this is more or less silt kind of category. So that is highly erodible. Then when you have 420 to 840 micron, about 1 mm or so, it is difficult to erodible. And third one is 840 micron to 6.4. So this is typically your in a way sand, and you can say the gravel kind of category. And more than 6.4 mm, which is gravel, which is non-erodible as per the typical classification. Now, the mechanism of soil erosion is crucial in case of wind erosion. Typically, there are three, you can say, mode of soil transportation. One is saltation, then second one is surface creep, and third one is the suspension. In case of saltation, basically when you have the uneven surfaces and you have the turbulent airflow, the air tries to lift the particles basically, and it involves bouncing and jumping within the air. So that happens. Surface creep is something that involves slow movement of the soil surface particles. Typically, in both the saltation and surface creep, typical range is 50 micron to 500 micron, 0.05 to zero point 0.5 mm. And whereas suspension is, the particles itself starts into the suspension mode with the air mass itself, and the particle size typically is zero point 0.1 mm. Now, whatever things I'm presenting, these are based on the RDSO guideline for erosion control. So I'm taking the direct reference from that literature. I'll be sharing different available literatures in Indian context. Coming back to the erosion using rain. So rain erosion is something where the rain droplets, when they, when the precipitation is there onto the slopes, there will be transportation of soil particles due to rainwater. So if we talk about the rain droplets, when it falls onto the on the top of the slopes, typically it tries to remove the or loosen the soil particles, And with that particular thing, there will be a resultant movement of the soil particles. As the water, gathers onto the slope, onto the, it forms a small catchment and it tries to formulate the path for, eroding the particles, taking it away from its original location. And it results into overall, you can say, kind of erosion where if the flow is concentrated, if the continuous watering is there on due to the rain, then there will be small rivulets, gully formation, erosion of, it would form the ditches which will, widen and deepen as the process goes on. Now, when this particular thing of rain erosion, if it is not arrested properly, in that case, um, slope would assume another geometry which is not intended for, and that geometry might not be suitable or stable in a way for the slope. So basically, when you have the cuts or gullies, your resisting mass in case of slope is, it's reducing, it's getting washed away, and that is where a typical slip circle, it forms into the soil. On the left side, you can see the image where the velocity of current in centimeter per second versus the size of grains is given. So when you have the very high velocities, let's say of the order 100 centimeter per second or more, then typically erosion can occur in almost all kind of soils, whether it is clay, silt, sand, or gravel. However, when the velocity is lower, 100 centimeter per second is like 1 meter, you can say 1 meter per second. That is very huge. It can erode almost everything. In the recent floods in Assam, you might have seen the pictures where, the complete railway bogies, those were pushed away from the tracks due to the flooding and this kind of heavy, you can say, heavy current situation. So it's quite likely that almost any kind of material would get eroded in this kind of heavy water current. So, in case of lower velocities, typically silt and clay would be the main prime type of soil which would typically get transported, and sand and gravel would be more or less into the deposition phase where they can where they can achieve their lowest possible energy levels. There they'll start depositing in that particular velocity. So this is the basic about rain erosion. When we talk about rain erosion, interestingly, we can divide a particular slope into three phases. First phase is zone of no erosion virtually. Basically, this zone is typically expected not to erode because you have front portion where we have a good amount of soil mass present, where one of the middle portion would be typically the zone of active erosion. Whatever erosion occurs in this zone would be getting deposited into this zone. And whatever, if the flow is continuous, then probably the soil mass after getting deposited here, if continuous rain is there, then it would be uh, along with water, it can uh, take place within the nearby channel. And this process typically continues as long as we have the erosion phenomenon. So, this is about the soil erosion. Now, soil erodibility is one of the main or major concern, you can say, in a way. So, soil erodibility is nothing but the susceptibility of a given soil to erode under the given erosiveness of the rainwater. So let us say if I'm having a low intensity rainfall, then the droplet diameter would be typically estimated to be around 1 mm or less, and the kinetic energy through which that erosion phenomena will occur would be very less. However, when the rainfall intensity is increasing to great extent, let's say 100 mm per hour, in that case, from just 2 joule per square meter per hour to it becomes around 3000 to 4500 joules per square meter per hour. And this is the critical factor. So basically, if we are trying to design for erosion control scheme, let's say in a very arid, or you can say the with very less rainfall intensity design area, probably let's say 15 mm per hour. we can take this particular energy into the account. Whereas if we are working with, let's say, very heavy, you can say the where you have excessive rainfalls or you have a very cloudburst kind of scenario, you can take this basically values for your design. Now, when we talk about the soil erodibility, it is quite obvious in a way. This is one of the classification which is widely used to summarize which type of soil is erodible, or you can say at least erodible. So, silt and silty sand, these two are the most erodible category of soils available. If we talk more about this particular thing, why erosion is a bigger concern in case of infrastructure projects. The specification, if you refer to the any of the you can say codal provisions, they'll be considering let's say silty sand or clayey sand or silty sand in general as a good material for construction, because you can have the proper, you can say, you can have the proper compaction in it. You will have the lower compressibility once it is constructed. So that material is suitable from the point of view of highway construction or embankment construction. But when it comes to the erosion, this is the most erodible material, and that is where problems start. So majority of the cases we have this material used for the embankments, and that's where we try to protect it using some of the techniques for erosion control, and often it fails basically when it is not properly taken care. So when we talk about most erodible, least erodible is somewhere, when you have a well-graded sand or gravel category. So that is typically least erodible for obvious reason that you have higher weight per particle, you can say. And that is where it becomes very difficult for rain particles to, do the erosion or move the particle. So, we have now developed a basic sense where we can say that we have understood the erosion to some extent. Wind and water is something that is going to create the erosion related issues. Gravity is going to support it in direct or indirect way, where, gravity can lead to slip circle related failures once you have erosion. So basically, now we have understood the erosion. We need to understand about the erosion control schemes, which are quite common, which we are in general we can adapt. So in past, where there were no good research available or no good solutions were available, vegetation was considered as one of the best thing for erosion control related activities. So that old is always gold, you can say. Bioengineering solutions using vegetation is one of the main or one of the best things that can that you can say is always better in a way. Uh, Now, in regions where vegetation cannot be grown, probably we can go with the conventional systems like stone pitching or cement stabilization, soil cement stabilization kind of, or and there are few other available solutions as well. And after this, there are engineered solutions. So basically, we have wide range of solutions available for this particular thing. If we want to simply add the different things, we can go with the, when we say bioengineering related solutions, we can go with the, let's say, living plants, grass. Vetiver grass is one of the options uh, which can be one of the very good options, because the strength of vetiver is very good. The roots in vetiver grass can be around up to 2 meters or so, which is quite huge, and that is one of the best options that is available for erosion control schemes. Availability of plant and the suitable atmosphere, these two are critical requirements for the living plants. When that kind of solutions are not available, many a times bitumen emulsion or liquid asphalt. In past, in few projects, this have also been adopted in past. There are few cement-based or rocky material-based or inert material-based, when you can say the kind of non-biodegradable solutions in a way. So those kind of things are there, gunite, concrete lining, fabriforms, articulated. Now, these conventional solutions in a way are not being used in recent days because of the limitation of available resources. Another critical issue is cost. When we go for cement, the cost is huge. So that is where this particular phenomena is not, it's not supporting in a way. Rocky material based, I think in next presentation, we'll be looking more into the Gibbon matrices or that kind of applications. Renault matrices and Gibbon matrices will be there. Other available options are gravel uh, pavements, or you can go for the rock ripraps. We'll be looking into one of the case studies and we'll be discussing in more details about that. There are few, inert materials which can be used like 2D mesh or net or cellulose fibers. So those kind of inert material can also be used for the erosion control schemes. So let's say which scheme is to be used. So this is the table given into the RDSO guideline for erosion control works. Now it gives the recommendations based on height of bank, whether it is less than 6 or whether it is higher than 6. So for a given, let's say silt and clay kind of category where the rainfall, the velocity of water is less than, let's say, 3 meter per second, we can go for the vegetation. If it is sandy or gravelly soil, we cannot grow the vegetation within this. So that's where we need to have a thin layer of, let's say, 0.25 to zero point 0.3 meter, about 1 feet of vegetative soil is required in this particular case. So this is the guideline which is given into it. Now, in case of banks or cutting less than 6 meter, so uh, this is again made of black cotton soil. So this is a recommendation. Now this is a rare case, but it can exist in case of when you have the vegetative lands at those locations. This is possible. So again, you need a good uh, clay layer, and you can have you can use the vegetation as one of the options. Now, when you have the height less than 6 meters, and if your problem is critical, probably we cannot use this particular guideline. We have to go for the customized solution for a site specific in this case. When you have bank or cutting in excess of 6 meter, then we have to go for a kind of reinforcement along with vegetation for the protection of, you can say, the erosion control system for the bank or the cutting. And for any other heights, the code is describing the boulder pitching with or without geotextile, geocell. Now, this guideline which I am presenting, it was published in the year 2005, and we are sitting here in 2024. So it's around about 20 years old. uh, a huge amount of work has been done in recent past, and different available solutions are there which can be used. So these two are the main codal provisions or guidelines we can say available for railway formations. Typically, guideline given by RDSO is the Ministry of Railways. This guideline is available, and in case of roads, we have guideline recommended into this thing. Now, there is a scientific approach. We call it the Russell formula, which I believe would be discussed by the other panelists in the next presentation. So I'm not covering that portion here. But that Russell formula is adapted into the IRC as well. It's universally adaptable. The soil loss equation is there, which would be discussed in the next session. So some of the generally adapted schemes, as we all know that this kind of, a kind of a cemented pitching, you can say in a way, this was used. There were many cases where probably this would not be suitable. We'll be looking into one of the case studies. Then you can have the vegetative facing, where we can have this kind of embankments. Then we can have embankments with, this is the typically, you can say, long slopes onto a landfill. I have taken this photograph just to demonstrate that we can have the coir mats, which can be laid over the slope, or we can have the geotextile laid over the slope, or we can have the geomats laid over the slope. We can have the when the slope is steep, we can probably go with the geogrids to make the slope stable. When you have any kind of vegetation, and when your slope stability is a concern, definitely you'll have to go with the engineered solution. So this is one of the options that we can take. Nowadays, this is geocells is also one of the common techniques that is being used in India. But unfortunately, when these are being placed, many a times failure occurs uh, due to various reasons. One is, when you have the very steep slopes, the soil, it gets eroded, and uh, the geocell becomes empty on the top, and that kind of things occur many times within geocell. You will have the connections, there will be tie clips would be there, which would get detached, and the a complete portion of geocell would get washed in that way. So those kind of issues are there. I hope soon those things would be either addressed or would be replaced with some other technology. Then you can have the geogrids or geomats. One point which I would like to highlight is whenever you have any reinforcement being used onto the slope along with the vegetation or anything else, this must be anchored within the anchor trench at the top, and that is where you are transferring the complete load of this particular slope, whatever loading is there into this particular material or whatever this thing. These are not only dependent on the soil mass here. It transfers load completely into the anchor trench, and that is where the loading onto this part, anything above this, would be little dependent on its overall geometry. It would be more dependent onto the this geogrid material or geomat material. These are typical Gaussian matrices, you can say, which are being used, which are being adopted. Now, we'll be looking into few of the typical failure cases where you have the, adapted erosion control schemes, but due to one or more reasons, when the applications are not understood properly, even though you have done a good amount of pitching here, this is a typical case somewhere down in south where this kind of closed pitching was done. There was nothing wrong with the technique that was adopted. The only thing was it was understood that the slope is one vertical to 2.5 horizontal. Material used was typically, core was clay. Then you had the kind of sandy material on the top of core, and then this pitching was done. So this should be stable. And if you are doing a basic engineering, you are not doing anything else, probably that slope should be stable. But whenever you are using anything within it, you have to be very, very careful. So in order to make this particular, this was a STP plant. So lagoon, this was the lagoon of STP plant, sewage treatment plant. So they wanted to make it impermeable. When you are trying to make it impermeable, typically available option is, let's say, geomembrane. When you're using the geomembrane, you have to be very, very careful, because in this particular portion, they had clay at the base, then they installed geomembrane, then they again placed the clay. So practically they made it a kind of zero friction value at the interface of geomembrane and clay. And when you are doing that particular thing, then whatever erosion control schemes you are making is of no use, because in principle you have made this embankment in such a way where it can simply slide onto the geomembrane itself. So geosynthetics, which we use, is definitely one of the best material or best technology we have. But if you don't use it properly, if you are not designing for the purpose, it could result into the failures. So this is again the same project at different. This was the central one that was on the end. This was at the edge, and this particular photograph is at the center. This is the center bund. And again, you have the failure of riprap. You have a huge settlement. You have almost sliding along this line. So basically, when we say that I'm designing an erosion control scheme, the point which I want to make here is you have to understand that erosion scheme often comes in combination with other schemes. It's not just erosion. If we talk about the slope stability, if you have slope, let's say 1 in 1.5, which is typically being practiced in India in highway projects, one vertical to 1.5 horizontal, which is about 33.5 degree. So when you have 33.5 degrees and the material which you are using, if it is, let's say, 26 degree or 30 degree or 31 degree, let's say 31 degree, and if you are putting it, let's say, at 33.5 degrees, in principle, when it is cohesionless soil, in principle, that has to fail. You cannot, even if you provide any kind of geosynthetic solution, or even if you provide any kind of solution in it, if slope is not stable, if your interface at which this particular sliding phenomena will occur, if that is not stable, this is going to fail. In most highway cases, people are simply using geocell and they are simply putting the material of high value, let's say 30 degree. And most of the cases, they suffer with the whole erosion control system, it gets washed away. So if you're designing something, see, more or less nowadays, GeoCell can be used if they are designed properly. You can always get the better results. But nowadays, these items are becoming commodity. They are no longer, solution in a way. If I know GeoCell, if I am visiting some site where I am having the GeoCells, I see how they are laying. So probably I'll consider myself as an expert, and then I'll start putting it in another project. So there is no involvement of designers in many occasions, and that is where it results into the failure. If I'm placing geocell at 26.56, one vertical to two horizontal with phi value 30 degree, and if I'm putting it, probably I should be, in that range where I can be successful. Now, if I'm putting it at, let's say, one vertical to one horizontal, 45 degree or 35 degrees, 33.5 degrees, it's going to fail. So that judgment basically is to be made, or the proper engineering calculation is to be made, without which there will be a huge amount of failures. Again, this is one of the cases where coir geotextiles kind of things were there. They had good vegetation in this within this zone, but since there was no anchoring and this particular mass in an event of rainfall, it started, kind of eroding. Now, if we look at this particular photograph, we have to understand that yes, this has occurred. Probable reason of failure of this particular roadway is due to erosion. But can I put any kind of erosion control scheme only just to make it sure that I'll be able to be okay with it? You can see that they had this particular earthen kind of portion, flat portion was available, then they had the slope. So this was the original scheme which was there. It had ample amount of vegetation. But when you have this kind of thing, probably within this zone, within this particular area, we need to ensure that there is a proper retaining system. Proper, you can say the steep slope was there, so that slope has to be stable. And if you are not having a stable slope, and if you are constructing something onto the top of this, we are obviously we are going to end up with this kind of accidents. And that is where we need to understand the importance of identifying the proper problem and then suggesting the proper solution for it. This is again one of the similar cases when you can say the highway is there, a good amount of vegetation is already there. You have, another small boundary, and this zone is, because this slope is steep, this portion is getting washed away during the erosion. And this is the phenomena, where we have to understand that probably this mass might not be stable just with the vegetation. You need to go with some kind of reinforcement within this zone so that you can make this particular slope stable, and it should be good enough to go for the its serviceability life. Again, this is one of the area, this is one of the portion. You can see the vegetation is there in the nearby area, this side and this side. This is a quite gentle slope in a way. But when you have this kind of valley on the other side and you have this kind of curvature, on both sides, they have probably, met this embankment. And when you have this kind of embankment on both side valley is there, then you cannot have the normal embankment. You have to go with some kind of proper, analysis for the slope stability, for proper, the toe protection, erosion control scheme. So only erosion control scheme is not going to work in this kind of systems. So you have to be sure, you have to involve an expert in your project. This see the main pain which contractors are having nowadays is whenever they are having this kind of embankments, they'll always end up with they have done everything perfect. They have done, they have executed their work, embankment, they have done very well. The surfacing is good, everything is very well. Because of this erosion control and maintenance, they are always suffering, and the uh, LD is being imposed onto the contractors just because they have not, and that condition where they have not done the proper erosion control scheme. Probably they have involved some designers or experts in that, but uh, those experts might not have taken the consideration of either the severity of the region in which they are dealing, or the kind of expected conditions. If they are not considering, or the application which they are not considering, then probably they'll end up with this kind of issues. So to summarize, there are few reasons for failure of erosion control schemes. We can summarize it as follow. Like first is negligence. In many cases, people work on a project where which are kind of item rate basis are there, or EPC basis are there. They'll say that my specification says I need to do this thing, and they'll go and try to find the cheapest option. They'll find they'll simply say, okay, geocell is written, or Gavian mattress is written, I'll simply buy from any person, and simply I'll put it without any kind of detailed designing or any kind of consideration. So this negligence plays a critical role. Second portion is cost. Nowadays these things are becoming commodity in a way. It's the harsh reality of the industry that people are, rather than focusing on a solution, they are simply trying to purchase the product from someone and simply put it. So that is when we work in L1 approach, then definitely contractor is trying to save each and every rupee, and then that's where they'll end up with this kind of issues. Second thing is design. Designing erosion control scheme is very simple in a way, but if it is not being designed properly, or if it is designed just based on experiences without taking the real data into the account, it would result into the failures. And many a times it is just designed for the erosion control, not for the associated factors like global stabilities or slope stability. So in that case, this can fail. Another thing is inappropriate construction. So we have seen that closed joint pitching in the project which I referred. They had lagoon, they had water, so they had to close the joints using cementitious material. But in many cases, because of the filling of those joints, the slope fails because water pressure gets developed within those zones, and it tries to dislocate, the complete system. So, when you are not using proper construction techniques or proper engineered solution, it results into the kind of failure. We have seen few of the photographs where, the stone pitching, sorry, the concrete was filled within the geocell. Now, in a way, the contractor tried to spend good amount of money into that. So they have used concrete and geocell, both the things. Ultimately, it could not survive because they have forgotten the basic principle that, anything, if you are putting this at, let's say, 45 degrees, this is not going to work because there is a soil lying beneath it, and the interface friction between the soil and geocell or soil to soil is much lower than the overall system which they are targeting, and that is where this kind of schemes fail. And another thing is the wrong combination of products. Now, using geosynthetics is not going to solve your problem. You have to use the right geosynthetics in right way, then only your overall scenario would be stable. If you're using geomembrane and you're using geonet, which is having the lowest possible angle of interface friction, then probably it's going to cost you a lot. You can, even if at 1 in 3 embankment, you will end up with failure. 1 in 3 embankment, I'm saying 18 degree. If you're using good soil, geonet would give you around 10 to 11 over on the top of, let's say, geomembrane if you're using. So if you are not using proper combination of products or proper geosynthetic solution, then it's going to be critical thing. So that's all from my side.
Thank you, Himanshu sir, for the nice presentation that we had. It was quite the interactive. So, moving on, we'll be moving to our second presentation for today's session. So, for this, I would like to invite Mr. Gianluca Spadaro to start with the second presentation. Mr. Gianluca is working as Business Development Manager at Officina Ferry, taking care about India and Southeast Asian and Pacific region. He has over 20 years of experience in geosynthetics and industrial minerals market, during which he has collaborated with most prominent companies in these sectors. I would like to call upon Mr. Gianluca to start this presentation.
Thank you for the introduction. Let's go ahead with our presentation. We will focus our attention today on erosion induced by rainfall and consequent runoff. We are not touching wet application. It means erosion induced by water flow. After a brief introduction on soil erosion process, we will recap briefly the different type of geosynthetic used in erosion control applications, included in the relevant norm, ISO norm. I refer to the ISO 18228 part 8, to have then a quick look onto our range of solution. Then we will go deep into the research commissioned to the University of Milan and the other research carried out along the year by our company, in order to identify the relation between erosion control product and vegetation growth, to identify the main factor affecting their vegetation success on slope. To go then through the design of our solution protecting slope from rainfall runoff induced erosion, according to the Russell approach that has been mentioned before, but by the previous panelist. And then finally, we will close with some case studies. Soil erosion is a soil degradation process, as has been mentioned before, consisting in the detachment of the topsoil due to the action of the natural forces. Once detachment would occur, soil particles are then transported away. Natural erosion occurs typically on a geological timescale, but when human activities modify the landscape, erosion process can be greatly accelerated. As we have mentioned before, we will focus our attention today in the today's presentation on rainfall and runoff induced erosion. Then water and wind are the two most common causes of soil erosion. Rainfall may generate the displacement of the soil particles close to the soil surface due to the impact of the raindrops, and runoff can be because of the carving of small rills and channels on erodible soil. And finally, strong winds may bring in suspension fine soil particles and may be cause of the movement by bouncing and rolling mechanism of the coarser one. Natural vegetation, if well established, is usually considered a sufficient protection against erosion. Vegetation coverage is typically able to protect topsoil from the action of the eroding agents, and plant roots are capable to hold in place vegetative soil, preventing it from being blown and washed away. Based on literature data, a vegetation coverage of 80% for clayey soil and 70% for sandy soil can be considered an acceptable protection against erosion processes on slope and embankment. The requirements in terms of vegetation coverage mentioned in the previous slide may be difficult to be reached on site. And even if reachable, there is anyway a time window until the full development of the vegetation, during which the soil is at the risk of erosion in case of intense rainfall. A paper from Rickson and Loveday reports that the full establishment of the vegetation may require 1 or 2 growing seasons in temperate climate, even longer on harsher sites. In tropical condition, full revegetation on a slope may take considerably less time. That's the reason why erosion control products made from synthetic or natural organic fibers are then frequently used in protecting slope from erosion and creating favorable conditions for the establishment and the development of the vegetation. Over the years, McAfee has been cooperating with some of the most important universities and testing institutes to develop sustainable erosion control solution, preventing soil loss and promoting the revegetation on slope and riverbanks. Along the presentation, we will go through the most relevant research and studies. Let me go through quickly to the classification of the erosion control products according to the relevant ISO norm. Again, ISO 18228 part 8. Geosynthetic addressed to erosion control application can be classified mainly based on product configuration, and then we may have GeoMat, GeoGrid, GeoWeb, and woven material in form of sheet material. Raw material can be also classified based on raw material from which they are made of, and basically erosion control products can be classified in based on natural fibers, typically jute or coir are the most common used raw material, or artificial synthetic fiber, typically polypropylene, polyethylene, and polyamide. And finally, geosynthetic used for erosion control application can be classified based on the duration of the protection against erosion. And then erosion control geosynthetic can be classified based on a permanent or a temporary duration. So it means it can be classified under permanent erosion revegetation materials, PERMs, or temporary erosion revegetation materials, terms. Let's focus the attention on the permanent one. Permanent erosion revegetation materials provide permanent protection against erosion, being manufactured using synthetic material, as we have seen before. To avoid any misunderstanding, when we are referring to the permanent action provided by PERMs, we refer to the action that can be provided by this type of material when properly filled with topsoil and shielded by the vegetation from the action, the degradation due to the UV radiation. Then, PERMs provide permanent protection against erosion, provide a support in the vegetative growth, creating favorable conditions to the development of the vegetation, and if well entangled with the vegetation, this provide also a reinforcement of the root system in terms of improvement of the shear resistance. Then, referring to this last feature, PERMs can be classified mainly in turf reinforcement mat, TRM, or ECRM, erosion control rolled material. We are referring to turf reinforcement mats if topsoil, cover soil, and seed are infilled inside the geomat. And then the vegetation can go through the geomat, getting roots can grow through the geomats, getting an improvement in terms of shear resistance. Instead of, we are referring to ECRM, erosion control rolled material, when the ECRM is laid on top of the slope without being infilled with topsoil and seeds. And then the vegetation can get only a reinforcement in terms of resistance only at the level of the stems, not at the level of the roots of the vegetation. Let me go quickly through the our range of solutions dedicated to erosion control. And again, we are referring just to erosion induced by rainfall and runoff. The name of the product dedicated to erosion control application in our product portfolio is MACMAT. MACMAT are geomats made of polypropylene monofilaments tangled together to form a three-dimensional, deformable mat having a thickness between 10 to 20 millimeter and having an high ratio of void. MACMAT being a PERMs, permanent erosion revegetation materials, provide a permanent long-term protection to the slope from the action of the eroding agents, support the establishment and the growth of the vegetation, increasing the shear resistance when infilled with soil and seeds. Then being, as we have seen before, based on the classification of the permanent erosion revegetation material being a turf reinforcement mat. Geomats can be reinforced by different type of polymeric geogrids or metallic grids. Let's have a look on the technical data sheet of the material just to highlight the main performances that a geomat shore lab must have in order to provide the proper performances in protecting slope from erosion due to rainfall and runoff. Light penetration is one of the most important properties in order to create favorable conditions to the germination process and then to the development of the vegetation along the slope. Ground coverage is something correlated to light penetration, because you can understand easily that an open material may provide a high value in terms of light penetration, ensuring the passage of a big portion of UV radiation, but at the same time, an open material may have a limited ground coverage and then a limited capability to protect the slope from the erosion areas. So it means that a proper balance between light penetration and ground coverage would ensure the best performances in terms of erosion control. And then we will see later, when we'll go through the Rasley formula, the C factor that is expressing the capability of the material to protect the slope from the erosion induced by the rainfall and runoff. And then finally, we will have also the performances, the environmental performances, since we need to develop, we are called to develop solutions that are sustainable under an environmental point of view. And the environmental performances, properties of our solution have to be independently verified and provided under an environmental product declaration. There's a document that communicating in a transparent and transparent way, in a comparable way, the information about the life cycle environmental impact of the product according to the relevant international standard. That's the environmental product declaration covering our product, providing the environmental impact of the product, referring to the production stage related to the raw material supply, transportation, and manufacturing. And then finally, the end of life stage and the benefits and flows beyond the system boundary at the end of the life of the product. Let's have a quick look into the research that we have mentioned before, that has been carried out by McAfee along the years in order to develop sustainable solution, preventing the soil loss and promoting the establishment and development of vegetation along slope and river banks. Which are the main factor influencing the establishment and development of vegetation on slope and embankment? To reply to this question, shown in the previous slide, we have commissioned to Professor Bischetti, head of the Department of Agricultural and Environmental Science at the University of Milan, our research focused on the relationship between erosion control product and revegetation and vegetation growth in order to identify the main factor affecting the revegetation success. The study identified 7 product-related factors influencing the revegetation success through 4 site-related factors. Product-related factors are light penetration, as we have mentioned before, thickness, color, water absorption, weight, roughness and runoff, and uniformity. The site-related factors are albedo, water runoff, soil humidity, and soil temperature. The performances provided by an erosion control product refer to complex processes resulting from the interaction of many different factors and features interacting each other. It's the balance between these factors that provide the best performances in terms of vegetation growth. It's not the huge value of one of these factors providing the best performance. It's the balance between the product-related factors. Erosion control products has been divided along the research into 4 categories: bionets, light geogrids, geomats, and geoblankets, based upon the origin of the raw material and the processing technique, the manufacturing technique adopted for their production. Bionets consist in biodimensional net made of biodegradable natural fibers. Light geogrids, the same, but done made of by synthetic fiber that can be multi-filament or extruded. And then geomats, we have been through this, the description of this type of categories when we have mentioned our MACMAT, that is a 3-dimensional geomats made of synthetic monofilaments tangled together and welded at contact point that can be also provided as it is or reinforced with synthetic geogrid or metallic mesh. And then finally we have geoblankets made of natural or synthetic fiber held together by synthetic or natural light geogrid. The performances of the 4 erosion control product categories identified in the previous slide has been evaluated in reference to the 7 product-related factors influencing the revegetation success that they have seen a few slides back. Then the effect of each product-related factor, again, light penetration, thickness, color, water absorption, weight, roughness, and uniformity, has been evaluated, has been associated to a value range between 1 and 3, where 1 corresponds to a detrimental feature having a negative effect on the development of vegetation. 2 correspond to a neutral feature having no effect on the development of vegetation, and 3 correspond to a positive feature having a beneficial effect on the development of the vegetation. The performances of the 4 product categories, again, bionets, light geogrids, geoblankets, and geomass has been represented through a radar chart representation. The value of each factor has been marked on the axis and then connected with a segment, creating a closed polygon that represents the radar chart. The area of the radar chart is directly correlated to the performances provided by the different product categories. So it means that the larger the area, the better is the performances of the erosion control product, really the relevant erosion control product. As you can see easily, the area correlated to the geomass is the larger one. So it means that geomass are able to provide the best performances in terms of erosion control. Our product fall in the geomass categories, but they have some differences, all of them affecting positively the revegetation success. I'm referring to color, since our product can be provided in different color according to the requirement of the specific project. As you can understand easily, black color are attracting UV radiation, light radiation, increasing temperature at the interface, instead of light color can attract on a lower side light radiation, reducing the temperature at the interface. Since our material can be provided in light color as well in dark color, can be easily adapted on the requirement of the specific project, instead of generally erosion control products like geomass are usually available in the market in only black color. Referring to weight, again, our MACMAT can provide better performances, since can be reinforced with a metallic mesh that is only related to the version where our MACMAT is reinforced using a metallic mesh that make our material capable to stay in tight adhesion with the cover soil, enhancing the germination process and then the development of the vegetation. Let me share a brief video. It is in Italian, but you can have the translation at the bottom. Related to the interview of the Professor Bischetti that carried out the research commissioned by our company.
Ci sono diversi fattori che in effetti quello che avevo voluto raggiungere. Sicuramente quelli più importanti sono legati all'inquinamento. Tra questi direi in particolare sono l'umidità, la temperatura e la luce. Questa situazione può essere influenzata da alcuni parametri controllativi, essenzialmente attraverso l'influenza di fattori di discriminazione. Quindi direi il Chemical Index, lo spessore, colore, il peso, la capacità di trattenere nell'acqua e l'uniformità spaziale e anche temporale. La condizione che hanno i giovani è basata principalmente sull'altro intervento, ma anche sullo spessore, sull'uniformità che sono state le caratteristiche, sono sicuramente i fattori che garantiscono meglio il successo. Nella categoria dei giovani è sicuramente alcune caratteristiche che hanno modo di vedere sono interessanti. Anche possibilità di cambiare colore, questo è un po' importante per le sistemi di temperatura, in ambienti è necessario e altre volte invece abbiamo la necessità di sfruttare il ragionamento solare. Una caratteristica che mi sembra molto interessante è quella di poter essere costruiti sulla presenza di una rete geosintetica telefonica, e questo permette di avere una buona combinazione tra tempo, spessore, elettronicità e un po' di contrastazione.
Just to summarize the things that we have been through when discussing the research at the University of Milan. Parallel to the research carried out at the University of Milan, mainly focused on to the, let me say, the agronomic aspects, we have carried out two separated testing campaigns, respectively at the Colorado State University, according to the ASTM D6460, and the TRI testing facility in the US, according to ASTM 6459, to check the performances of our MACMAT range in protecting slope and riverbanks, respectively, from rainfall and runoff-induced erosion, according to the relevant standard, and the erosion induced by water flow, by storm water. Both standards require full large-scale testing procedure. The testing campaign conducted at the Colorado State University, even if performed carried out according to standard evaluating the performances of the erosion control product in protecting riverbank from stormwater-induced erosion, give us an additional confirmation about the capability of our product to provide the condition to have a full revegetation in very short time. So it means that in only after has been proved through this testing campaign that in only 6 weeks our product has been able to reach 60% of the performances at 1 year time. So it means that in relatively short amount of time, MACMAT would have been able to ensure a revegetation achieving at least 60% of the performances that can be achieved in 1 year. But let's focus our attention, as we have discussed before, on erosion induced by rainfall and runoff. So it means on dry erosion. Erosion control solution design typically suffer from a lack of, let me say, rigorous scientific approach. The selection process of the different type of erosion control products available in the market, in most of the cases, is driven by the knowledge according to previous experience, instead of monitoring and modeling erosion processes may contribute to have a better understanding of the causes of the soil erosion processes, making at the same time soil loss prediction more reliable and helping in the identification of the preventive strategies to control it. The most common model for predicting soil loss induced by the action of rainfall and the consequent runoff on slope is the Russell equation. So it means the revised universal soil loss equation that has been issued in the late 60s by the Agriculture Department of the US. The Russell equation provides a prediction of the soil loss due to sheet and reel erosion on slope. It can be then used to identify the most critical areas subjected to erosion and to estimate, at the same time, also the benefits provided by the corrective measure under evaluation. The Russell equation is expressed by the formula that is shown in the slide, where A is the estimated average soil loss, R is the rainfall and runoff erosivity factor, K is the soil erodibility factor, L and S are the slope, length, and steep factor, C is the cover management factor, and P the support practice factor. Let me go through the different factors providing the estimation of the soil loss according to the Russell equation. R is the rainfall runoff erosivity factor and depends on local and regional rainfall. R factor value can be estimated strictly based on local regional pluviometer readings. However, there are many empirical formulas available based on statistical analysis of many years of pluviometer readings, and in some cases validated through direct erosion measurement, providing an evaluation of the R factor. K is the soil erodibility factor and express the tendency of the soil to be eroded and depends on the soil texture. It means a different percentage of a different type of soil, clay, silt, sand, and gravel, and the soil hydraulic conductivity. As for R factor, also K factor can be evaluated, estimated using empirical formulas. Then we have slope length and slope steepness factor, L and S, that refer, as you can easily understand, to the length, respectively to the length and the steepness of the slope that are affecting the erosion on the slope under evaluation. Then finally, we have the most important factor, the C factor, that represents impact of the cover and management system. Cover refers to the type of the density of the vegetation along the slope under evaluation. Instead of management system relate to the erosion control technique that has been used to protect the slope from erosion. As we have seen before, the C factor can be estimated only through full-scale or large-scale lab test when a slope protected with the erosion control product under evaluation. There's a picture of the test conductor on our material, our MACMAT, protecting a slope subjected to a rain simulator. Then C is back calculated after the evaluation of the soil loss that can be collecting the soil loss at the bottom of the slope. P, finally, is the support practice factor, reflecting the impact of landscaping and agricultural practices adopted to reduce the erosion potential of the runoff, such as contour farming, strip cropping, terracing, that may modify the flow, pattern, direction, and the volume of the runoff. Support practice factor, P, is typically taken equal to 1 in a construction project to be in a conservative position. As mentioned in the previous intervention, Russell approaching something not new for Indian standard, finally is already mentioned and included in ERC 56 as an evaluation of the soil loss. Just to give you a brief indication about the soil loss connected to an unprotected slope or a slope protected with our MACMAT, referring to a fill slope having a length of 20 meters and inclination of 30 degrees, taking in consideration a duration of 1 year, the erosion evaluated in terms of soil loss, ton per year, would be 570 ton in case of unprotected slope without any protection on top, and in case of the same slope but protected with our MACMAT R1005, the soil loss would be considerably less, a little bit more than 14 tons. You can see the huge difference between the two values. Russell approach is already implemented in our EcoMac design, implemented in our eDesign platform, evaluating the soil loss and also the stability of our product, our MACMAT on slope and riverbanks. Let me briefly close with some case studies. First case study refers to the application of our MACMAT in protecting from erosion the cut slope along the railway connecting Dar es Salaam and Morogoro in Tanzania. This was the first section of the line connecting Tanzania, Congo, passing through Uganda and Rwanda to give them access to the Indian Ocean. The picture showed the rills and gullies carved into the side slope of the railway by the runoff induced by intense rainfall. The original solution proposed by the consultant of the contractor involved in the project to protect the cut slope from the erosion was based on geocells. The slides show the failure of the solution tested in a dedicated area with the geocell exposed, partially empty, and without any development of vegetation on the top. If the slope inclination indicated as alpha in the slide is lower than the angle of repose of the soil, provided the application of an adequate erosion, a proper erosion control product on the top of the geocell to protect the infill material from the action of the eroding agents, a solution based on geocell may work properly. Instead of, if the slope inclination is higher than the angle of repose of the infill soil, as soon the slope will be subjected to the action of the eroding agents, the infill soil will tend to accommodate accordingly to its natural angle of repose, leading to the failure of the solution based on geocell. That's the reason why the solution proposed originally by the contractor failed. We have been then requested by the contractor to support the consultant in the definition of an alternative solution, and we have then proposed the application of our MACMAT in combination with hydroseeding. The picture is related to the results of a test, a trial, done on site to evaluate the effectiveness of the proposed solution. On this section, with the vegetation on top, it has been installed our MACMAT, and then it has been done the hydroseedings. On the right, just bare soil, only shaped, and on the left, again, bare soil, shaped, and then hydroseeded. Picture, I think, is self-explaining. Then here we have some picture related to the installation of our MACMAT, starting from the anchoring trench on the top that can be done by excavating a small anchoring trench, or anchoring can be done by the application of a proper number, an adequate number of steel pins, like the J1 shown in the slide. Then the mat has to be properly installed on the slope, taking care to ensure a tight adhesion between the geomass and the soil, to ensure the most favorable condition to the germination of the seeds and then the development of the vegetation. Again, a picture related to the installation of our MACMAT reinforced with the T-mesh on a steep slope. And then finally, the hydroseeding carried out using a specific mix of seeds defined according to the project site condition, such as exposure, precipitation, irradiation, light irradiation, and so on. And then the results on the slope some weeks after. I think, again, self-explaining. Then let me pass to another case history of a project done in Russia. Again, protecting the side railway line slope with our MACMAT. Let me sorry. Okay. Let me show a brief video giving an overview. Oh, something went wrong. Let me see if now it's working properly. Yeah, the video provided an overview of the project. You can see the side slope of the railway before the intervention, in this case, with no development of vegetation. And then finally, we will have the overview during installation, of course, and after the installation with the same slope protected with our MACMAT. In this case, has been used our MACMAT reinforced with the DT mesh due to the inclination of the slope, according to the indication that we have received from the consultant involved in the project. There's some detail related to the installation of the material, as we have seen before, anchoring the material with the anchoring trench or with some J steel pins. Railway line has been constructed in order to connect the this gas plant and the Trans-Siberian line in order to get the different part of the plant to be transported on site. That was really important to ensure that the railway will not suffer from any issue correlated to the erosion of the side slope. Length of the slope was more than 50 meters, in some cases with an height of more than 26 meters. That's the reason why there's been used our magnetic reinforcement with the DT. This is some something related to the production of the material. Again, the installation, the material has been not hydroseeded, but just covered with topsoil. The project involved the installation of more than 640,000 square meter of material that has been produced in our plant in Russia. And then the material has been, as you can see, this is the package of the material, protecting the material from the degradation due to the UV radiation. The installation of material requires typically 4 or 5 workers in order to cut the material and to install the material properly along the slope. And taking care about the shaping of the slope, at least 10 centimeters of cover soil has to be removed and then shaped in order to ensure a proper base for the installation of the material. As we have seen before, the anchoring trench on the top, typically 30 centimeters deep, should be enough. And then the rolls are installed along the slope in order to ensure the continuity between the adjacent rolls. Material need to be properly pinned on the edges and in the middle, typically, in order to ensure, as we have seen before, a tight adhesion of the material along the slope in order to ensure the proper condition to get the germination of the seeds and then the development of vegetation. Typically, production is between 3 and 5,000 square meters per shift, according to the setup that I've seen before, requiring between 4 and 5 works per shift. In this case, material has been covered with 30 centimeters, but typically it's not required a so huge thickness. Typically, just the material can be just filled with some cover soil, not more than this. The material is added with carbon black in order to stabilize the material along the installation, but material, as we have seen before, to provide long-term performance need to be covered with topsoil and shielded by vegetation. Then let me close with a case history related to the protection of the side slope of the Amasya Highway. We are in the northern part of Turkey. The Amasya Highway has been cut through a mountainous area. Fine soil and frequent rainfalls results in superficial sliding, affecting the safety of the route and forcing the authorities to close the road from time to time for cleaning roads. There's a picture related to the installation of the material that before we have seen magmat black color, and instead of we have material available in light brown color in order to moderate the increase of the temperature due to the UV radiation that particularly high in this region. Then the installation of the material, putting the adhesion rods and pins typically on the edges and in the middle in order to ensure a tight adhesion between the material and the soil and the slope. And finally, a picture related to the first phase of the revegetation of the slope after the hydroseeding process. So finally, we have reached the end of the presentation. Thank you for your attention, and then I will leave to the organization to pass to the next panelist. Thank you for your attention.
Thank you, Mr. Gianluca, for the detailed presentation. So now we'll be quickly moving on to our third presentation for today's session. For this, I would like to call upon Dr. Ratnakar R. Mahajan. Dr. Mahajan is alumnus of IIT Bombay and working as Regional Technical Manager at Mecca Ferry, responsible for India, Southeast Asia, and Pacific markets. He is a civil engineer with key experience in soil reinforcement, ground improvement, retaining structures, slope stability, river training, channel lining, and rockfall protection works. So, Dr. Ratnakar, you may start the presentation.
To all of you. Thank you, Himanshu and Jaluka, for introducing the topic and making my most of the presentation very easy. So, soil, of course, is very precious material. Basically, we are importantly using soil for everything from getting our food to most of the activities. So it's a very, very important material which we must conserve, because nowadays, because of the activities what are being carried out or the environment change, we are losing the very precious material, that's soil. If we lose the soil, then we will have very difficulties in getting most of our materials required. The formation of soil requires number of years weathering, and then what you get is a fertile soil. So, from our school days that if you have the rocks, they are exposed to various kinds of the weathering actions related to the sun, temperature, water, air, rain, and then finally we get the fertile soil. So that's why it's very important to conserve the soil. This photograph, you can very well see that there is a soil erosion happening. On the left and right side of the photograph, you see the vegetation is being established. So it's very important to understand the main role of erosion protection of the soil will be provided by vegetation. Now, for getting the vegetation, whatever we can do or whatever is required to be done is to be done. So here, the idea is to provide the erosion protection using a natural material, that is a vegetation. It can be in the form of a grass or bushes or any other form. Of course, soil erosion is a natural process which occurs like Himanshu and Jaluka has explained because of the detachment and movement of topsoil, which could be by wind or action of wind or flowing water. Now, due to the, let's say, not proper attention being provided or timely not being provided, so this kind of issues can accelerate and erosion can happen. Of course, there have been some instances where embankment slope, irrespective of which type of soiling is being used, they have suffered very high degree of damage. So like Himanshu explained, various types of soils, and the type of soil actually is related to the type of resistance or the amount of resistance it provides related to the erosion. Of course, the inundation of vegetation from soil slopes, which lacks in the vegetative cover, is often reasonable for formation of the rill cuts or rain cuts, eventually leading to the superficial slide and sometimes even the deeper slides. Of course, when you provide the erosion control, the main objective is to protect these embankments. It could be any infrastructure, could be road, railway, or any other infrastructure, so that it continues and functioning, permitting the uninterrupted service. Could be related to the traffic or design speed. Of course, to preserve the earthwork in fill, which is typically either it could be fill or cut, or prevent the damage to the adjacent land area, or to reduce the soil loss from the embankments, which basically seals into drainage channels. Of course, once you have the drainage channels being filled up, there are issues related to drainage, finally could lead to the failure of the slopes. Very important part, sometimes you need the improvement in the aesthetics of the landscape or to avoid the accidental falling of debris. Some photographs from the Indian Road Congress 56 document. So you can see here formation of a rill erosion on an embankment which is subjected to the very high rainfall, and these rills can even further go and form deep gullies. So this rill or deep gullies is formation is related to the raindrops. Of course, when you have the raindrop falling, it comes with certain kinetic energy, and then you have the splashing of the raindrops, or it can roll down the water surface, flow sheet of water, bringing down the water. So the velocity of water will increase along the slope and the drag force on the soil particles. If adhesion or the cohesion between particles is less than the drag force, then the soil particles also tries to move along the water and detachment of soil particles happen. To prevent erosion, one of the advanced method is providing erosion control mat. Of course, you can combine it with the hydro mulching. So typically, this is what you have an issue, of formation of the rills or gullies. Another issue is when you have the embankments which are flooded during, let's say, certain part of the year or throughout the year, then you may have erosion at the toe or at least area where the flood water touches the embankments. Or you have flash floods, and then you may have completely the washout of the embankments. This photograph is from one of the project in the Rajasthan, and you can see the type of soil, which is cohesion-less, and you can find here the accumulation of the ballast itself. So this is a railway track under construction. This is the ballast. Due to the rainfall, the cohesive soil, non-cohesive soil has basically eroded, and formation of deep gullies has formed. At the same time, even the part of the ballast also has been brought it down. Some portion of the same area where the treatment was done with the plantation, typically the sodding, still it's not so effective. So you all must have seen these kind of channels on the slope. These gullies are formed on the slope due to the erosion, and if you don't provide erosion protection measure on the slope, then you can find such kind of situations, which are typically a deep gullies formation. This is another photograph from a project of an soil construction, where again you use non-cohesive type of fill, and Due to the concentrated water flows, you can have formation of the deep gullies as well as the rill erosion. So what are the different options of erosion control? Of course, you can have simple vegetative turfing, or you have ready-made grass turf which are being prepared, and then they are transported to the site and then you apply them. However, for big infrastructure works, there is a limitation. If it is a small area, typically in the architectural works, you may have the lawns being transported. Then it's possible because the area is very small. Or you can have application of mulch. So you have mixing of water, the seeds, and the special mulch with some binders, and then you spray it. Or possible solutions are vetiver grass. That's also being commonly used. Vetiver grass are known for very deep roots. The roots can go deep as around 5 to 6 meters. However, successful establishments of vetiver grass will give you the correct erosion control solution. Of course, you can have the jute or coir knittings, which can help in protection of embankment temporary till the vegetation is growth. After the vegetation is grown, of course, over a period of time, these are biodegradable materials which will biodegrade and provide the manure also. Or you can have three-dimensional erosion control mats or rolled erosion control products. You can have geocells or webs or the armor system. So very common solution adopted is a riprap, where you have the stones which you can place on embankment. However, stone is a precious material. Quarrying itself is a challenge, and then you transport it. All parts of the country, you may not have this precious material. The construction of this riprap is also requiring a skill. Another option is you may use the concrete blocks. Of course, cement is one of the material which is commonly used in the civil construction. However, the cement is again one of the major contributor for the greenhouse gases. If you just research, you will find how much damage it does. So it's better to avoid using such kind of materials. Another option could be using a concrete mattresses. However, the issues could remain same. You are using concrete, which is contribution to the greenhouse gases, and we need to look at for the sustainable solutions, which are greener solutions, or you may use geocells, but like Jaluka explained, if you use geocell filled with soil, if they are not covered with proper erosion control on the top, if they are installed on the steep slopes, then you will have certain issues. Of course, I want to show some photographs where the photographs are self-explanatory, like the project where the geocells have been installed and erosion protection, and you can see here completely the soil filled in the cells have been washed away because of the surface runoff. Certain portion there was a concentrated flows, and even there is a deep scours happening, and even the failure of the whole embankment, failure of the erosion control measure, which were in the form of a geocell that's being pushed. Another photograph of a project of a national highway. You can see here, this is an embankment which is protected with geocell filled with soil, and you can see where you have the concentrated flow. Completely the soil filled with the geocell, or even below that, has been completely washed off. So the effectiveness of such solution is really difficult to ascertain until unless you have, let's say, if in this portion you would had a erosion control mat on top, so the mat would have provided the temporary protection for erosion control. Same project where you have concentrated flow, you can see it itself, the washing of the complete soil layers. Another popular solution which is now being practiced is geocell filled with concrete. So you have a slope and then you install geocell and fill it with concrete. However, geocell, the function is basically confinement of the soil itself. But when you put a concrete, does concrete require any confinement? No, because the concrete, that is a mixture of cement, sand, and aggregate, it provides a binding material together and forms a complete cohesive material. But if you place this concrete material in a geocell, you are providing discontinuities completely. The walls of geocell will provide discontinuities, and there is no proper flexibility remaining in this solution. So if there is a scouring happening below that, or the soil erosion happening below that, then overall whole solution is not working properly. And you can see here, if I just zoom in here, you can see the lines of the geocell or the walls of the geocell providing real picture how the geocell is being installed, and then no more the concrete is homogeneous. If you just place the PCC itself, that would be more than enough rather than providing the the geocell filled with the concrete. This is a close-up view of it, you know, and you can see here even the gaps which are all around the soil cells of the geocell are finding the ways where the vegetation is growing, you know. So it's better to provide the vegetation itself rather than going with this, fancy solutions. Jaluka and Himanshu, the earlier panelists, have explained about IRC 56. I just want to talk here. You know, in erosion control, the practice overall is okay. How it works? It works for me, then I will practice. You know, that's the overall practice till now it is. But as engineers, we need to move from the work practice to, let's say, engineered approach. As 56 talks about a soil loss analysis. What it means is, if you have an embankment and if you have the let's say rainfall, how much amount of soil will be eroded? Let's quantify that, and then you bring up erosion control measure, and then how effective it be, how effective it would be. Then you again estimate the soil loss and compare the estimation of the soil loss without any protection and with protection, and then you compare it, and then you will get the efficacy of the the erosion control measure. Same document, it talks about the energy of falling raindrop, and then how exactly the kinetic energy will of the raindrop will basically yield in the kind of erosion, whether it is a sheet wash erosion or your splashing, you know. Same document talks about the Russell, that is a universal soil loss equation, and then it is called as the Russell equation, that is revised universal soil loss equation, which was given by Renard in 1997. As Jaluka explained, the amount of soil loss, the computed soil loss in tons per acre for a given storm period and for a given time interval, let's say tons per acre or per hectare per year or per whatever time year you want. So it's typically maybe ton per square kilometer per year. It depends on you what you want to estimate. So in this equation, there are different terms which already explained by earlier panelists, R, K, L, S, C, T. All these terms, if you see, R is a factor of, let's say, precipitation. K is depending on the soil. L and S is depending on the slope and length. C is a vegetation crop factor, and P is the erosion control practice factor. Now, if you see whole this equation, all terms remain constant for a particular site except the C. C is a vegetation crop factor. As explained earlier, it can be estimated by using a full-scale test. That's what being carried out at the TRI. Of course, as McAfee, several tests have been performed on the MacMet in order to study the erosion control mechanism. Over the years, McAfee has been working along with some of the most prominent universities and international level to develop sustainable solutions to prevent the loss of soil and enhance the vegetation. Of course, the important part of selection of the erosion control solution, especially with the mats, is basically these factors what already being explained related to the light penetration, the color, thickness, weight, and uniformity. Very important part is the C, which is the cover management factor, which can be estimated using laboratory test or full-scale test using ASTM D6459, you know. With this, of course, I don't want to again repeat what Jaluka and Himanshu has explained, but I want to show you some Indian case histories where you can see the approach has been an engineering approach, and I think it's a time we need to practice this Russell equation where you need to have this C factor. Of course, the C factor can be estimated for various kinds of erosion control solutions, what you may practice. And then you estimate the amount of soil loss, and whichever solution gives you the least amount of soil loss, you adopt this solution. So this is a project which was for a client water resources department. This was along the Gandak River. Gandak River, which originates from Nepal, enters in India. Here a barrage was being constructed. Along the length of this river, there were issues related to the severe erosion due to the flowing water as well as the rainfall. In the photograph, what you see is basically embankment portion which is stabilized, and you can see the first photograph dressing of the slope, and the second photograph installation of mat are, and this is what the a retaining wall that's being constructed along the length of river. This is where the Gandak River near Valmiki Nagar in Bihar. Due to high flow during monsoon, the left river bank has suffered severe erosion. Here, reinforced soil walls were being provided as a toe, and the reinforced mat was proposed to protect the slope against the erosion. Here, of course, as I explained, due to high flow, there was an issue related to the toe of the slope. Here, the solution of mat was combined with the hydromulching. The hydromulching was provided with the Macflex and Manganix, which are basically soil amendments, and they are combined with the MacMat, which is conforming to the Ministry of Road Transport Highway specification as well as the ISC 56 specification. Basically, this MacMat acts as a turf reinforcement, which create an environment to develop vegetation and reduce the velocity of water on the slope surface, absorb the impacts of raindrops, also reducing the splash effect, and acts as a reinforcement for the roots of the vegetation. So around 19,000 square meter of the MacMat was being installed. Another project in the state of Rajasthan for a railway embankment. So like earlier photographs where I showed the formation of gullies. So this is the embankment, this was the situation, and you can see the type of soil here used for building the embankment. Here, first the hydro mulching was done, followed by installation of a MacMat R. In this area, the client has tried multiple options like fire, jute, synthetic mats, as well as the vetiver. Of course, one of these trials with the synthetic mat gave really good performance. However, adoption of such solutions usually is related to the cost. However, I would like to mention cost shall not be looked into the initial cost, which is usually done by engineers. We shall get away from this. The cost shall be understood initial cost as well as during the lifetime of or the design life of the structure, how would be the maintenance cost? Because if you install such a solution which is cheaper at the initial, but if it doesn't work for over a period of time, and then you will have an issue related to the maintenance cost. In this project, the embankment heights were around 12 to 18 meter. Here, of course, denudation of vegetation from soil slopes and lack of vegetation cover, often responsible for formation of frills and cuts. That's what we have seen. Here, of course, the applied solution was the hydraulically applied erosion control, that is HECP, along with MacMat 9.1. That's what's being applied. This is another project from Northeast Frontier Railway. Here there was a cutting. On the cutting, the fire mats were being installed, and you can see the nice establishment of vegetation. However, if you talk about the amount of soil loss estimation, it's a difficult one to estimate because unless you have the C factor, you cannot estimate. However, if you do the full scale test and then as per ASTM, then you can estimate the soil loss. This is another project which is done on the railway embankment, where you can see first the dressing of slope, then watering, then spraying the mulch, then the establishment of vegetation. This is another project where for a northern railway near Lucknow, the embankment was required to be protected using the any means. So we propose the basically MAC mats. So here, first photograph you can see here, dressing of the slope followed by the hydro mulching, then watering, and then of course here the MAC mat are that's being installed. So you see these solutions are not only uh, establishing vegetation but pleasing, aesthetically pleasing, and of course providing back the green solution, the absorbing the carbon from the environment, and that's how they are greener solutions. So these are the basically the approvals from RVNL for these both projects. Another project where the cut slope stabilization, where the slopes were cut at very steep angles, 30 to 87 degrees. This were between Kerala, Tamil Nadu border at Veliguri section. The slopes were required to be stabilized using the nails, but certain portion of the embankment were required to be protected from the erosion. Here, again, hydro mulching and the MACMAT were being installed as a erosion control solution. Another project for a railway embankment where the railway embankment were facing an issue of surfacial stability where self-drilling anchors were installed. And then on top of these embankments, the basically MACMAT HS 100 valve installed combined with the hydro mulching. So this is the photograph of initial site condition, and then this is what after the stabilization of the slope. So of course, we are always side by side with engineers where we are getting involved from stage of initial planning to the execution, where our experts can help in selecting these kind of solutions. So very important part, as I said, environmental sustainability we need to understand. Geosynthetics, of course, reduce the environmental burden, which is achieved by ease of installation, increasing of speed of construction, of course, where you reduce the running of machineries, improved performance and longevity. Of course, as I explained, cost, we shall not see look into the initial cost, but also the overall cost. So application of geosynthetic construction improves the sustainability in terms of conserving the natural materials like soil and the environments. Of course, it's important to go for a holistic approach of erosion control solution. Here, most tested and tried solutions like MACMAT can be used. It's one of the best erosion control solution. As I explained in the beginning, we need to approach it through the engineering approach, understanding the soil loss, and then selecting the solution. With this, I thank you for patiently listening, and over to moderator.
Thank you, Dr. Ratnakar. Thank you for the quick presentation. So now we are towards the end of the session, and now we'll be taking the Q&A round. So we'll be taking a couple of questions due to paucity of time, and we will start with Mr. Himanshu Kotak. So now we have our first question, and question is how can we prevent soil erosion cost effectively? So this is the first question that we have.
Right. So, to answer that, uh, we need to first understand the term cost effectiveness. We have to do the life cycle analysis of a slope, its expected erosion, uh, the kind of material that we have within the nearby area, the availability of different uh, kind of materials for slope itself. So it's not an easy thing to do. Let's say if I'm planning to, let's say I'm having a slope of 1 vertical to 2.5 horizontal, and if I want to do stone pitching, if it's a area where rocks are easily available, probably that would be the most economical option. But let's say if the slope is flat, but I'm not having stones available, then I'll have to go for alternative solution. So it's dependable, it depends on the location to location, and site specific study must be done for each and every case, and designs can be done accordingly. If I'm not having the sufficient material, I can go for steeper slopes. Let's say if I'm going for 1 vertical to 1 horizontal 45-degree slopes, but in that case slope cannot be just constructed using soils, just embankment. we'll have to go for reinforced soil slope. So basically optimization and optimization of erosion control scheme itself is a vast topic, and it should be dealt from site to site, location to location.
Okay, thank you. Thank you, Himanshu sir, for this question, for taking this question. So now we will move to our second question, and this question is from Mr. Gianluca Spadaro. Question is, what are specific outcomes of UNIML research, and please explain conclusion of the research. Mr. Spadaro, you are on mute. You need to unmute yourself, please.
Yeah, sure. Sorry. Just unmuted. Yeah, the research carried out by the University of Milan was focused on the relation between erosion control products that we have seen along the presentation has been classified into 4 main categories: bionets, geogrids, geomats, and geoblankets. Then the relation between the erosion control product considered along the research and the revegetation success along the slope, in order to identify the main factor affecting the revegetation success, improving the revegetation success. Then, along the research, geomats has been identified as the erosion control products able to provide the best performances in terms of protection against erosion, and in the meantime creating favorable condition to the development vegetation along the slope. That's the main outcome of the research, that geomats has been identified as the best erosion control products in order to protecting slope from erosion and creating favorable conditions to the vegetation. Hope it is clear.
Thank you for taking this question. So we'll be taking our last question for today's sessions. And for all the unattended question, we urge you that we'll be providing the questions via email, answers via email. So before taking our final question, so I would like to request that there is a feedback form that we have placed in the chat box. We request everyone to attend that. It helps us improving our upcoming sessions. So now the third question that we have is for Dr. Ratnakar or Mahajan. Question is, as shown in the images earlier presentation, geocell were damaged due to concentrated water flow along the slope. Why can't this happen to MAD proposed? This question is from Mr. Shrijit VK. Sir, you are not audible. Dr. Mahajan? Can you mute and mute yourself once? Not audible, sir.
Am I audible now?
Yes, you are, sir.
Okay. So thank you very much for the interesting question. I think the question is, what will happen if there is a concentrated flow? Okay, now we will need to understand how the mechanics of these mats and let's say the geocell is. You have a slope surface. Now on slope surface you are putting a mat. This mat is a 3-dimensional mat with the fibers, and which has certain thickness. Now imagine you have a water flowing or surface runoff over this mat. Now these mat fibers provide a resistance, where the water will basically reduce its flow. Now you have a sheet of water, so there is a water which will have higher velocities at the top. So if you recall any open channel flow, the water velocity is not constant throughout the channel. It is highest at the top and it reduces, and at the bottom it's the lowest one. Now here we are putting a mat which is again providing the higher shear resistance. Now with this higher shear resistance, it will reduce the velocity, it will reduce the shear stresses, and the detachment of the soil particle will reduce. Whereas in case of geocell, where you have geocell filled with soil, the water is moving on top of it, where the soil particles are no more confined. The water is directly moving on the soil surface, eroding the soil itself. On top of that, these mats have been tested, let's say what Jaluka has presented, in 3 different conditions. One in open water channels. So we have tested these mats for even open water channels. These mats can sustain the water flow around, let's say 2 to 3 meter per second for a particular time interval. So these mats also can be used in an open channel itself as a lining itself. Secondly, these mats have been tested for estimation of the let's say the C factor, the effect, the C factor in the Russell's equation, and the mats have tested for different rainfall intensities like 50, 100, and 150 mm per hour. So we have tested these mats for rainfalls of different rainfall intensity. And of course, if you are estimating or putting the mats directly under very high flow like a river, then of course it's not going to work. We are talking of embankments. We're talking of the concentrated flows coming from these embankments. So surely these mats can take this kind of concentrated flow, subjected to the different kind of rainfall intensities what we have tested in different conditions.
Thank you, Dr. Ratnakar, for taking this question. So with this, we are ending our today's session. We hope that you all found this session interactive and it was as fruitful for you as it was for us. And I'm again mentioning that there is a feedback form that is in the chat box. We request everyone to attend that. And also you can follow us on our social media handle on X, Facebook, LinkedIn. So we are sharing our upcoming webinars, success stories, and latest happening at our company. So thank you all.
Thank you.
Thank you.
Thank you. Thank you for your time.